Here's a quick walkthrough of the homework problems from section 1.3 that ask for examples of things with explanations. The largest epsilon neighborhood of 2 that fits in the interval. Remember, these are all open sets, and so epsilon equals 3 would be fine. You don't have to do 2.9 or 2.99. It works fine. The interval, that's 3 less than epsilon and 3 less than x naught and 3 more than x naught would be the interval -1, 5, and -1, 5 open interval is a subset of -infinity to 5 open interval. Neither one of them pretends to have the number 5 in them, and so it's completely cool to have epsilon equal 3. The second one, we're trying to give an example of a set that's neither open or closed, and so most people were okay with this. The open interval, the interval that's open on one side and closed on the other side should do this, but please make sure that you can give an explanation based on the meanings of the words. So, for example, closed sets, we had a theorem that said that closed sets include all their limit points, but the interval 1, 4 has 1 as a limit point, and so 1's not in there, so this is not a closed set. The set's not open because the number 4 is not an interior point of the set, and that's because there's no neighborhood about 4 that's completely included in the set. This one, I think, was the hardest one for people to write down. I really didn't even understand what a lot of you were writing. Infinitely many closed sets whose union might not be closed, and so your example has to be infinitely many closed sets. For example, here's a bunch of closed intervals. Those closed intervals look like this. So when n is 1, this will be 1 minus 1 is 0. So this is the closed interval -1, 0, union closed interval -1, 1/2. That's what this would be. If n was 2, closed interval -1, 2/3, closed interval -1, 3/4, and so on. Surely the left-hand side is closed interval minus, but the right-hand side, as these upper numbers get closer and closer and closer to 1, you're not going to be able to cut this side off at any point below 1, but you're not including 1, because if 1 were in here, then 1 would have to be in one of these, and it's not. 1 is not in any of these sets. And so the union is this thing, and so that's not closed. So for many of you, I couldn't even find the infinitely many sets or the union, much less an explanation of why the union closed. But try to, this is a case where you probably were trying to tell me and I just didn't understand the notation you were using. An example of a set where the infimum is not a limit point. Most people just tacked a isolated point to the left of some other set, and that's perfectly fine. This example also works fine. Notice that these numbers are increasing, and so the smallest number is the first number, so the infimum here. But 0 is not a limit point. The only limit point for the set S is where those numbers are headed, which is 1. But make sure I say the definition. 0 is not a limit point of this set because here's a deleted neighborhood, and this is a way we can express the deleted neighborhood. It's an open interval where I subtract out the center of it. So that's a deleted neighborhood of 0, and surely that set contains nothing that's in S. Right? It almost goes up to the first number. But there's nothing in S that's also in this set. And so that means that 0 is not a limit point of this set. These things with the boundary, this is hard to even make it ever be true. So just about anything you wrote down would be right as long as you understood what the boundary meant. So here's 2 open intervals that overlap. So their boundaries are just their edges. So -2, 4 and 1, 8 are the boundaries of these two. That's supposed to be an S2 right there. So these are the boundaries of the two sets individually, but since they overlap, when you do the intersection, you get another open interval, and the boundary of that open interval are its two ends. And so that is not the same as that. In fact, this is empty. So anyway, so it's something like that. This is about interiors, and so what we need is something where the interior of the union has some more stuff in it than the union of the interiors. And so we can do that by having intervals that mesh right up against each other. And so like these two sets are intervals, and they sort of meet at x equals 2. Their interiors are the open sets. And so you see when you take the interior of them separately, we are leaving out 2 entirely. That's supposed to be S2. Wasn't very diligent about my subscripts. That's S2. But if you take the union of these two sets, you just get the open interval 0, 5. And so the fact that 2 sat at the ends of these guys is erased. It disappears from the information about the union. And so that means that the interior of the union is just 0, 5, but the union of the interiors leave out the point 2. So it's not the same thing.